Hopefully by now you can appreciate a little bit of the conundrum in which cosmologists find themselves. On the one hand, we have a theory that fits the data, the theory of dark energy being 70% of the universe, along with 25% dark matter and 5% ordinary matter. If that dark energy is vacuum energy, if it is strictly constant, 10 to the minus 8th ergs in every cubic centimeter of space, unchanging as the universe expands, we can explain a whole bunch of observed phenomena all at once. We explain the flatness of space. We explain the fact that the universe is accelerating as a function of time. But then when we dig into that idea a little bit and start asking about how quantum field theory and our understanding of gravity would predict an energy density for empty space, we get a number, that prediction, that is bigger than what we actually observe by a factor of 10 to the 120. A 1 followed by 120 zeros. This is the cosmological constant problem, the biggest issue right now in all of theoretical physics. So what we used to believe, before we thought that there really was dark energy in the universe, is that the reason why the vacuum energy was small is because it is exactly zero. Because there's some secret symmetry, some dynamical mechanism that we haven't yet discovered, which takes what we think should be a large vacuum energy and squelches it all the way to zero. Now we're in a slightly trickier situation. We want to squelch it most of the way, but not all the way there. One of the plausible scenarios is a two-step process. One that says the actual vacuum energy really is zero. It is still true that there is some unknown mechanism which sets the vacuum energy exactly to zero. We haven't found it yet, but we'll still be looking. And then we explain the dark energy by some separate mechanism, by some other form of stuff that acts dark energy-like. In other words, it is more or less the same in every different cubic centimeter of space and more or less constant through time, but not strictly so. Something that can slowly change or gradually fluctuate from place to place. This would be a dynamical kind of dark energy, something that is temporary, something that can eventually go to zero. It might be, in such a universe, that in the future there won't be any dark energy anymore. One of the nice things about this possibility is that you can go test it. If the dark energy is not strictly constant, it is observationally distinguishable from the absolutely constant vacuum energy. So what we want to do is to try to make some specific models, some theories of what a dynamical dark energy could be, and then test them against other things that we can observe in the universe. It's not hard to come up with models for dark energy that are dynamical. The simplest idea is one called Quintessence, and it just fills the universe with a new kind of field. We know that the standard model already tells us that the universe is made of fields. There's a field for the electron, there's a field for the photon, the electromagnetic field, and so forth. So if we want to add new physics, we're going to start adding new fields. What are the properties that we want this particular new kind of field to have? Well, for one thing, we want it to be a boson. If the field were a fermion, it would take up space, so you could only have one new quintessence fermion in any one place. We want there to be a smooth distribution all over the place with a whole bunch of quintessence, relatively speaking, so we want it to be a boson. We also wanted to not pick out any preferred direction in the universe. If you think about some of the other fields that we know and love, like the electromagnetic field, when the electromagnetic field is turned on, the electric field is pointing somewhere. But the universe looks the same in every direction. So we want the quintessence field to not pick out a direction in space. Physicists call such a field a scalar field, a field that just has a value everywhere. It's just a number. It is not a little arrow or a little vector pointing in some direction. The really crucial property the quintessence should have is that it should evolve very, very slowly. What this means is the observations are telling us that the amount of dark energy is more or less constant as the universe expands. Now, if you have a scalar field, if you have a field that has energy, is a boson, does not pick out any preferred direction, there are scalar fields in the standard model. There's the Higgs field. But the Higgs field does not slowly evolve as the universe expands. It dramatically goes down to the bottom of its potential and just sits there. The Higgs field is not contributing any slowly changing dynamical contribution to the dark energy. So we previously offered an analogy to what a field is like. It's like a pendulum swinging back and forth, but there's a pendulum at every single point in space, rocking back and forth, and then the different physics of the different fields corresponds to what that pendulum couples to, what its amplitude is, and so forth. So in other words, what we really want for quintessence is a pendulum that is almost stuck at some non-zero value and is going down very, very, very slowly, as if it's a pendulum stuck in very, very cold molasses and it cannot evolve very quickly. Well, we know how to do that. Physicists know how to write down theories that have bosonic fields, fields that can pile up, that move very, very slowly, that have energy densities that don't change very much as a function of time. However, for better or for worse, it changes the situation compared to if you only had vacuum energy. Vacuum energy is just a number. It's a value, which observationally is something like 10 to the minus 8 ergs per cubic centimeter, which tells you the minimum amount of energy in every single place in the universe if there's no stuff there. That number doesn't change. There's nothing that number can do other than make the universe accelerate and otherwise have a gravitational field. But if you're adding an entirely new field to nature, that field has dynamics, it can interact. That's good because you can measure things about it, you can test it. It's interesting because those dynamics might have interesting new features, but it can also be problematic if those interactions have already been ruled out. So let me just mention one thing that you might want the quintessence field to do, one motivation for considering some dynamical feature of dark energy rather than just something that is absolutely constant. That motivation is called the coincidence scandal. The coincidence scandal is just the fact that in the current universe, what we're claiming is that the dark energy is 70% of the total energy density. The matter density, both dark plus ordinary, is about 30%. 70% and 30% are not that different. And in the traditional cosmological evolution, these numbers change with respect to each other dramatically as the universe expands. So the energy density in dark energy is more or less constant from moment to moment. The energy density in matter is plummeting. As the universe expands, the number of particles per cubic centimeter is going down as the volume goes up. So you have two numbers, the density of matter and the density of dark energy. They're changing dramatically with respect to each other, yet today they are the same to within a factor of about 2 or 3. The dark energy is about 2 or 3 times bigger than the matter density. Why are we so fortunate to be living in just that moment of the history of the universe when the dark energy and the matter have comparable densities to each other? If you like, think about what life would have been like back at recombination. At the moment when the microwave background was being formed, the universe had a scale factor, a size, which was 1/1000th of its current size. At that moment, at recombination, the density of matter divided by the density of dark energy would be 1 billion. There was 1 billion times more energy density in matter than in dark energy. That's a completely typical number. You're not surprised if you get a number like 1 billion. You're surprised if you get a number like 2, because if a number changes from being a huge number in the past to being a really, really tiny number in the future, there's something special about now. Ever since cosmologists realized that the Earth is not the center of the solar system, and Copernicus put us at the edge, we've been very, very wary of any theory that says there's something special about us in space or as a function of time. But the coincidence scandal says exactly that. If you have an absolutely constant vacuum energy, then it's very difficult to think what you could possibly do about the coincidence scandal. There's nothing that changes in that vacuum energy. There's no mechanism that makes it kick in at any particular time in the universe's history. It's set by hand in the very early universe, and then you just get lucky later on. Now, we'll later discuss the possibility that the vacuum energy is very, very different in very different parts of the universe, parts we don't observe, and therefore you might get some explanation for the coincidence scandal within the context of a constant vacuum energy. But if you don't believe that, if you believe that what you see in the universe is the kind of universe you get everywhere, then to have any hope of explaining the coincidence scandal dynamically through some mechanism rather than just through saying, well, we got lucky, you need to give the dark energy itself some kind of dynamics. And that's what quintessence does. That's what the possibility of dynamical dark energy tries to do. Now, I'll make a confession. The confession is that even though it was a motivation for thinking about quintessence, attempts to actually explain the coincidence scandal by using quintessence haven't really worked. People have tried to invent theories where the energy density in quintessence didn't used to be constant. It used to decline very, very rapidly in the early universe, just like the density in ordinary matter or radiation. But then something changed relatively recently in the universe's history. For example, the formation of galaxies. Galaxies didn't exist when the universe was 1/1000th its current size. Maybe when galaxies started to form, something changed in the dynamics of the quintessence to make it stop evolving. That's more of a hope than an idea right now. There's not really any theoretical models that make that happen, but that's the kind of thing that cosmologists are looking for. Right now, I can't, in good conscience, point to any models that actually make that happen, but that's not to say that tomorrow morning one won't appear on my desk. This is the kind of thing that we're trying to think of right now in the context of dynamical dark energy. Another thing is that the future of the universe could be very different if you believe in dynamical dark energy. The analogy I gave for quintessence is a pendulum that is going down very, very slowly because it's stuck in molasses. But if the energy density of the dark energy is allowed to change, then we should be open-minded. We know almost nothing about the energy density of the dark energy or the fundamental physics behind it, and therefore if we can invent theories in which the dark energy is gradually fading away as a function of time, why not consider theories where the dark energy density is gradually growing as a function of time? Now, that's not to say it's easy to invent such theories, but once again, we can do it. Physicists know how to write down equations governing the behavior of a dark energy field for which the density would go up. So not only the total amount of dark energy because the universe is expanding, but the amount of dark energy in every cubic centimeter would gradually be going up as the universe expands. This is a very dramatic idea which has been given the name of phantom energy, but it leads to a very dramatic consequence, which is why most people are interested in it. If you have an energy density in empty space that is growing, and it continues to grow into the future, remember that what the dark energy does is to impart a constant impulse to the expansion of space. So if the amount of dark energy is increasing, and it's constantly giving an impulse to the expansion of space, the expansion rate will be increasing. The actual Hubble parameter will be going up. Space will be expanding faster and faster, and you can reach a singularity in a finite amount of years into the future. A singularity in which everything is ripped apart. Individual galaxies, planets, and individual atoms are ripped apart by a huge amount of energy density in empty space. This has been called the Big Rip to be a possible future evolution of the universe, in contrast with the Big Bang that we had at the beginning. A singularity to cap off the end of the universe, just like there was a singularity that started it. All of this is completely hypothetical. There's no evidence that we have right now that something like the Big Rip would be happening. In fact, there are important physics worries about these models. If you can have energy grow, what that means is that if you look at the excitations of this field, if you look at the particles that you would see if you actually observed the quintessence field directly, what you would see are particles with negative energy. So in otherwise empty space, you could spontaneously create some positive energy particles and some negative energy particles without violating conservation of energy. That's never been seen. It would mean that lighter particles could decay into heavier particles by emitting particles with negative energy. That's never been seen. So the possibility of phantom energy is not a leading candidate. Most physicists are kind of either scared or appalled by the idea, but it's the kind of thing that we're driven to think about because we know so little about the underlying physics of dark energy. So it's the kind of thing to keep in mind about what the possibilities include. Now let's go a little bit more down to earth and ask, if there is dynamical dark energy, what does that get us? Who cares? Can we somehow do something with it in terms of observational constraints on what it is doing? And the answer, asked in that way, is of course yes. Once we have a field, not just a number that is the same everywhere, but a field that can vary from place to place and has some dynamics of its own, that field can interact. The dark energy field, the quintessence field, can interact with ordinary matter, it can interact with dark matter, or both. A whole bunch of opportunities open up. Well, how would you notice if the quintessence field was interacting with ordinary matter? Remember, the quintessence field is a number that is slowly changing everywhere in space, slowly rolling down some potential field so that its energy density is gradually evolving as the universe expands. So two things are evolving. One is the value of the field. The other is the amount of energy contained within that field. Every given theory is going to tell you, for a given value of the field, how much energy is contained in it. But because the field itself is evolving, its interactions with all of the rest of nature mean that there will be hidden effects on the rest of the particles, for example, in the standard model. For example, you would expect, if you were in a background field that was slowly changing, for things like the mass of the electron and the charge of the electron to be gradually changing as this field evolved. It's not necessary. You can certainly invent models in which that doesn't happen, but the default assumption is that would happen. So in other words, you can look for quintessence directly in the behavior of ordinary matter by asking if the so-called constants of nature are truly constant or if they're changing. As it turns out, we have a lot of data that tell us that the constants of nature are the same now as they were in the past. If you go all the way back to Big Bang nucleosynthesis, a minute after the Big Bang, we have made very precise predictions for the abundance of helium, lithium, and deuterium on the basis of our current knowledge of nuclear and atomic physics. Now, if something were different, if the mass of the proton were different during Big Bang nucleosynthesis, you would predict, in principle, very different abundances for the light elements. So the fact that you get the right answer in conventional nucleosynthesis tells us that the constants of nature at that very, very early time were more or less the same as they are now. There are similar phenomena that we don't have time to go into in great detail. There's something called the Oklo natural reactor, which was a naturally forming formation in Gabon, West Africa, where there was a self-sustaining nuclear chain reaction. Billions of years before Enrico Fermi put up the first man-made chain reaction outside of the University of Chicago, nature did it itself, turning heavy uranium into lighter elements, and we can go there today and measure the reaction products. We find results that are consistent with the hypothesis that the constants of nature back then are the same to within 1 part in 10 million as they are today. So the data are telling us that as far as we can tell, the constants of nature 2 billion years ago are the same values as they are today. Quintessence would tell us that it would be very, very plausible for them to have changed. That's not a rock-steady limit. It is not absolutely ruling out the idea that there is quintessence, but it's putting some pressure on it. If there had been quintessence, maybe we should have seen it already in something like the decay of the constants of nature. The other possibility, if quintessence interacts with ordinary matter, are new forces. Remember, bosonic fields give rise to forces, the photon, the graviton, the gluon, etc. Furthermore, there is a rule that says the range of the force, the spatial distance over which the force can stretch, depends on the mass of the boson that is carrying that force. The forces that we know in nature that go over long range are the gravitational force and the electromagnetic force. These are the ones that we can see in our macroscopic everyday lives. The reason why these stretch over long distances is because the bosons that carry them, the graviton and the photon, are massless. If the bosons are massive, they give rise to very short-range forces. And that kind of makes sense. It just takes energy for the boson to stretch over a large distance. If it has a large mass, it's not going to stretch very far. So what about quintessence? Quintessence is a boson that has a very small mass, very close to zero. If the mass were large, it would have fallen to the bottom of its energy already, and it would not be evolving. By hypothesis, the quintessence does not have a large mass. Therefore, it should give rise to a long-range force. This would be what particle physicists call a fifth force of nature, because we already have gravity, electromagnetism, the strong and weak nuclear forces. This would be a new force, and a new force that stretches over macroscopic distances. It would be kind of like gravity, a weak new force, except that unlike gravity, it would not be universal. The secret to gravity is that everything falls in the same way. Every object, regardless of what it is made of, feels exactly the same gravitational force. If quintessence exists, it gives rise to a new force, but one that affects different objects differently. So we're actually looking for exactly that. Experiments are going on to measure the acceleration of little balls made of different substances in the direction of the sun. We are able to measure the force due to gravity of balls here on Earth caused by the sun by looking at how much they move in that direction at some time of day versus another time of day. And we can do this again and again with different kinds of substances. What we find is that there's no evidence for a new force of nature that depends on the composition of the different kinds of stuff you're dealing with. So once again, it is not saying that quintessence doesn't exist, but there was a chance for us to find it in fifth force experiments, and we haven't found it. The supposition needs to be that if quintessence is there, somehow it is hiding from us, somehow there is some symmetry or some dynamical mechanism that is preventing us from directly detecting the quintessence in any obvious way. However, I don't want to be too pessimistic about things. I want to emphasize the fact that we are just beginning to measure the physics of the dark sector. We're proposing that 95% of the universe is made of stuff that we haven't directly seen. Dark matter, 25%, dark energy, 70%. The model we have right now that fits the data is a very minimal, vanilla kind of model. It says that the dark energy is strictly constant and doesn't interact with either ordinary matter or dark matter except through gravity. The dark matter is completely non-interacting, 25%, and doesn't interact with dark energy or with ordinary matter except through gravity. That is a model that fits the data. But again, we're nowhere close to having completely figured out the physics of dark matter and dark energy, so we could be seeing something much more dramatic. 100 years from now, we might have a whole rich phenomenology of the different kinds of interactions that characterize the physics of dark matter interacting with ordinary matter, dark energy interacting with dark matter, and ordinary matter interacting with dark energy. We're just at the beginning of thinking about these things, so we don't know what's going to come until we go out there and look. I should mention that quintessence, the idea of a single field slowly rolling down, is not the only way we could imagine getting dynamical dark energy. It is by far the leading candidate. It's very easy to write it down. It's very easy to come up with specific models that fit the data. But there are alternatives. For example, there's the idea of tangled strings in the universe. We will talk about superstrings, very, very tiny strings whose vibrations look like elementary particles. There are also cosmic strings, a very, very different idea, strings that stretch across the observed universe. We haven't seen any of these things yet, but if the cosmic strings are relatively light, we would not have seen them. If the cosmic strings have the property that when two strings bump into each other, they get tangled, the total energy density in cosmic strings can evolve very slowly, if at all. In other words, they can be something like dark energy. It turns out that when you run the numbers, the actual energy density, even in tangled cosmic strings, seems to go down too quickly to be the dark energy. But again, maybe that's just because there's something we're missing in the models. It's something to keep in mind. The other possibility is something I like very much because I helped invent it. It's the possibility of variable mass particles. What if you really, really wanted to believe that the dark energy, just like the dark matter, was made of particles? The real problem with believing that is that particles, slowly moving particles, have an energy, E equals mc squared, that doesn't change as a function of time. Since the energy per particle doesn't change, as the universe expands, the energy density goes down, and that's not what dark energy does. But imagine that you had particles whose masses went up as the universe expanded. In other words, the energy per particle was still E equals mc squared, but the mass was going up just like the number density was going down. Then you could have the total energy density in this kind of stuff act like dark energy. These variable mass particles, or VAMPs as we called them, could be a kind of particle that didn't have its energy density go away as the universe expanded. The bad news is, in the details it doesn't quite work. You might want to ask, how should the mass change? What is governing the value of the mass of each particle? What you would do is you invent a scalar field. You would invent a field that governs the mass of the particles, and that would basically act just like quintessence. It turns out that the idea of variable mass particles is not really a separate idea from quintessence. It's a way in which you can have the dark matter particles interact with the dark energy field, which is something interesting to think about. So far, it's not something that is pushed upon us by the data, but it might be there, so we're still looking. So let me finish up by talking about how we would know, how we can actually go about testing this idea that the dark energy is dynamical, not strictly constant. Well, the way that we found the dark energy in the first place was to look at the acceleration of the universe. If the dark energy weren't dark energy, if it were just matter, you would have a decelerating universe as all the particles in the universe pulled on all the other particles, and the universe would expand but ever more slowly as time went on. When the dark energy kicks in, it's a constant energy density that provides an impulse to the universe, and we see acceleration. So if you imagine that the dark energy is slightly dynamical, if the energy density is not strictly constant, but slowly changing, then you still get acceleration, but you get a slightly different rate of acceleration than you would with vacuum energy, a strictly constant amount of energy density in empty space. So cosmologists have invented a number to characterize how much the dark energy density evolves as the universe expands. For weird historical reasons, they call this number the equation of state parameter, and they label it W. Remember when we talked about the way in which dark energy evolves and the reason why it makes the universe accelerate, we said that one way to think about the fact that the dark energy makes the universe accelerate was to say that it has a negative pressure. And the thing that makes the space expand is the energy density plus 3 times the pressure. So ordinary dark energy in the sense of vacuum energy, something that is strictly constant, has a pressure which is exactly equal but opposite to its energy density. Pressure equals -1 times the energy density. The idea of W, the equation of state parameter, is just to replace that -1 by an arbitrary number called W. If W is very close to -1, then the dark energy density is almost not evolving. If W is a little bit greater than -1, which, because -1 is a negative number, means something like -0.8 or -0.9, that means that the energy density will slowly be declining. That's the obvious guess, if you believe in quintessence, is that the equation of state parameter should be a little bit greater than -1, because the energy density in dark energy should be slowly going down as the quintessence field evolves. But it could be slightly going up. The dark energy density could be going up if you get phantom energy, so it could be that W, the equation of state parameter, is less than -1. It could be -1.1 or -1.2. How would you know? Well, you look at the data, the same kinds of data we use to discover the acceleration of the universe, and you fit it to a different kind of model. What we used to do was to fit the data to a model in which you had both matter and dark energy. The dark energy was constant, but the total sum of the two was arbitrary. And then you asked what fit the data. The thing that fits the data is something where the total amount of energy is the critical density and space is flat. So you get a 2-parameter family of possibilities: how much dark matter, how much dark energy. You can replace that with a different 2-parameter family of possibilities by assuming that space is flat. Assume that the total amount of dark energy plus the total amount of matter equals the critical density. Then the 2 parameters you now have are the total amount of matter, which determines the total amount of dark energy, and the equation of state parameter, and W, which tells you how fast the dark energy evolves. If that's true and you plug into the data, you get limits on what W is. Right now, that limit is something like W is -1 plus or minus 0.3. So to a good confidence level, W is somewhere between -0.7 and -1.3. On the one hand, that's telling us that it's close to -1. The dark energy density is not evolving very appreciably as a function of time. On the other hand, it's telling us that there is room for improvement. Certainly, if the equation of state parameter was -1.1, we would not have noticed it yet, or if it were -0.9. So we want to do better. Perhaps the biggest single experimental project in modern cosmology is trying to measure the equation of state parameter to higher precision. We'll talk in Lecture 23 about a suite of new experiments that are trying to pin down the equation of state parameter to plus or minus 0.05, to plus or minus 0.05 to 5% instead of plus or minus 0.3. To do that will require a lot more data, perhaps going to space, certainly building things here on Earth. We will do it, though, and it's very important to do it, because the kind of physics that you invoke to explain constant energy density in empty space versus variable energy density is completely different. We may never know which one is right. We may get really unlucky. If the true equation of state of the dark energy in the real world is minus 0.99, it is hard to imagine how we will ever tell that it's not exactly -1. But in the meantime, we can hope that we're a little bit luckier than that we'll keep measuring it better and better, and pretty soon, if it comes closer and closer to being -1, we'll be able to say, yes, indeed, the dark energy that is 70% of the universe is the vacuum energy of empty space itself.